Good morning. Happy Thursday. Hope everybody's doing well this morning. So we are going to pick up where we left off in section 3.7. We got 3 examples left to do in that section, and then we'll get into 3.9. Between today and Monday, we'll definitely be able to finish up those 2 sections and have time to go through the practice test. I don't know exactly how far we'll get into 3.9 today, but whatever we don't finish, we will finish on Monday, and then we'll still be able to review. So the test will be posted Monday at midnight, due Wednesday at midnight. Don't forget also that you have the homework on sections 3.4 and 3.5 that are due by midnight tonight. And then that 3.7 and 3.9 homework will either be due Monday night or Tuesday night. So again, you've at least got the weekend. We'll kind of play it by ear, see how far we get into 3.9 today. If we don't get far enough, then I might push that back to Tuesday. Okay. But again, the test will definitely be due Wednesday at midnight. So just be planning on that. Find yourself some time Tuesday or Wednesday that you can sit down and take that test. Okay. Any questions, comments, concerns about anything that's coming up right now? All right, so like I said, we're in 3.7 optimization problems. So remember yesterday we looked at that first problem. We were trying to optimize the area inside of a fence, right? And so we said, well, the first thing you always want to do, you can sketch the picture. Then you want to figure out what formulas you're going to have to use, try to get everything in terms of the same variable. Then we take our derivative because we know we're looking for a maximum or a minimum, and that's how we find a max or a min, is by taking that derivative. Okay, so we're going to do the same thing on all these optimization problems. So here we've got a cylindrical can. We want to make it hold 1 liter of oil. We need to find the dimensions that will minimize the cost of the metal to manufacture that can. So what do you think we should do first? All right, good. Let's sketch the picture, right? So what are we going to draw this time? It's a cylinder, right? Okay, so make sure we're sketching a cylinder this time. Sorry, give me 1 second. There we go. All right, so I'm going to draw my cylinder over here now. And again, we don't know the exact dimensions, right? So any old cylinder will do. Looks something like this. So there's my cylinder. All right, now, what do we know about this cylinder? All right, it needs to hold 1 liter of oil, so the volume needs to be 1 liter, right? So we've got a volume of 1 liter. What are we trying to find? We need the dimensions, right? So if we're looking for dimensions, we're going to need, all right, good. So we know there's a volume formula for a cylinder that's pi r squared, that's the area of the base, times the height. So we're going to use volume equals pi r squared h, which means the dimensions we're looking for are the radius and the height, right? Those are the 2 things we're going to have to figure out this time. Well, that means in my picture here, I'm going to go ahead and put my radius on here. So the radius is going to be right here, and then the height of our cylinder is going to be over here. So those are the 2 dimensions we need to know. All right, now, what do you think we might want to do next? All right, now, before we take the derivative, remember on the previous problem, if we can get everything in terms of the same variable, that's going to be our best bet, right? Okay, now, Also, what are we trying to minimize this time? The cost, right? Which means that we actually want to minimize what? What would we want to minimize if we want to minimize the amount of cost? The surface area, right? Because if we can minimize the amount of surface area on this thing, we're going to minimize the amount of material that's needed. That will minimize our cost. So we actually want to minimize surface area. So we're going to need the area formula for this cylinder. How would you find surface area for a cylinder? All right. Almost. You just left out your pi's, right? Okay, but yeah, everything else there looks good. So we're going to do 2 pi r squared, because pi r squared is the area of a circle, right? So that's going to give us one circular base. We multiply that by 2. That gives us the 2 circles, the top and bottom of our cylinder. Then we need to add that area around the outside of the can. Well, if you think about it, if we were to take that and unwrap it, right, and fold it flat, it's going to make a rectangle. The dimensions of that rectangle, the height is h, right, and then the other piece is just going to be whatever the circumference is of that circle once we unwrap it. To find the circumference, we're going to use 2 pi r. So we're going to do 2 pi r times h. So the 2 pi r squared gives us the 2 circles, and then the 2 pi r h gives us that outside piece that wraps around. All right, so there's our surface area formula for a cylinder. Now, if that's the thing we're trying to minimize, that's the thing we're going to take the derivative of, right? But again, we need to try to get everything in terms of the same variable first. So what information do we have now that's going to help us to get everything in terms of the same variable in our surface area formula so that we can take the derivative? Okay, good. We know what the volume is, right? So we can actually solve that then by plugging in volume and then solving for one of our variables. Before you do that, though, we don't want to plug in 1 liter because liters are definitely liquid, right? And we're looking for radius and height. We need linear dimensions here. So we need to think about what that volume actually is in terms of a linear dimension instead. So does anybody know a different way to write 1 liter in terms of linear dimensions? If you've ever had a chemistry class or something, you've probably seen a conversion like this before. Anybody know what 1 liter is equal to? Okay, so 1 liter is actually the same as 1,000 cubic centimeters. Okay, so whenever you see a liter, you can think of that as 1,000 centimeters cubed. That way, we actually have something that's in terms of centimeters now, so that when we find our radius and our height, we get centimeters out of that. Okay, so we can't just use 1 liter because that's a liquid. We need something that's in terms of a linear unit. Okay, so now that volume formula, I'm going to put 1,000 equals pi r squared h. All right, now what variable do you want to solve for here? All right, so if we solve for h, we're just going to divide them by the pi r squared. So that's going to give us 1,000 over pi r squared equals h. All right, now what can we do? Good. Now we can substitute that h value into our surface area equation That way we have everything in terms of r. So this is still going to be 2 pi r squared, but now this becomes 2 pi r times 1,000 over pi r squared. All right, now before we take our derivative, let's see if we can simplify this a little bit. So again, the first term here is definitely 2 pi r squared. Can't do anything with that. If we simplify this over here, though, what's that going to give us? Good, right? So the pi's are going to cancel. The 2 times 1,000 gives us a 2,000. And then one of those r's cancels out, but we still have an r left over in the denominator. So now we just have 2,000 over r. Any questions about that? Okay, now, if we're going to take the derivative of this, what do you think we should do first? Good. Move the r up and make it a negative exponent. That way we can use our power rule. So this is going to be 2 pi r squared plus 2,000 r to the negative 1 power. Now let's find our derivative. So what's that first term going to give us if we use our power rule now? Good. So the 2 times 2 gives us 4 pi. Subtract 1 from your exponent. That's just 4 pi r. And then the second term here is going to give us what? Good. So we got a negative 2,000, because again, we're multiplying the negative 1 times the 2,000. And then we're going to subtract 1 from the exponent. So that becomes a negative 2 now. All right, so there's our derivative. Now, if you wanted to, you could go ahead and move that r to the negative 2 into the denominator. It's probably actually going to be easier in this case to leave it like this because we know we're going to do what next? We're trying to find the minimum. Okay, so think back to that first example. We were trying to maximize our area inside the fence on the last one, right? And so once we took the derivative, what did we have to do next? Set it equal to 0. Good. It's the same thing here, right? We're looking for a minimum value. We need to find the critical numbers. So we're going to go ahead and set this equal to 0 now. Now, since we're setting it equal to 0, we probably want to factor the right-hand side. So let's think about how we could factor this. What's something that these terms have in common? They definitely have a 4, right? And they have an r to some power. Now, when you're looking for common factors, remember we always look for the lowest possible exponent. What's the lowest possible exponent this time? Negative 2, right? So we're going to factor out 4r to the negative 2. Now let's think about what's left over if we do that. In this first term here, if I factor out the 4 and then I factor out an r to the negative 2, what's going to be left over from that first term? Okay, so there's definitely going to be a pi. But I only had an r there, and I factored out r to the negative 2. So what else do we need with the pi on that first term? R cubed, right? Because if you were to redistribute this now, r to the negative 2 times r to the third, 3 minus 2 would give us r to the first power. Okay, so just keep in mind we do need an r cubed for that first term. Then we have our minus. We factored out 4, and we factored out r to the negative 2. So that's going to leave us with 500. Perfect. Any questions about the factoring there? All right. Now, once we have our factors, now we can do what? Set each factor equal to 0. I'm going to rewrite 4r to the negative 2 now as 4 over r squared. Set that equal to 0. And then we're going to do pi r cubed minus 500. Set that equal to 0. All right, so if we look at this first one here, 4 over r squared equals 0. How would you solve that? Okay, now before you could take a square root though, right, that r squared's in the denominator. So what would you really have to do first here? You'd have to multiply by r squared, which would give you what? 0, right? And you'd still be left with the 4 on the left-hand side. Is 4 ever going to equal 0? No, right? So this one right here, you could either say no solution or does not exist, right? We're not going to get any r values here where 4 divided by r squared is going to give us 0. It's not. Okay? Now, to solve the other one, though, what are we going to do first? Okay, good. Move the 500 over, so we get pi r cubed equals 500. Then we can do what? Divide by the pi. So r cubed equals 500 over pi. And then we can do what? Take the cube root. Good. So we have r equals the cubed root of 500 over pi. Now, if you wanted to know an approximation for that, right, obviously you could put cube root of 500 divided by pi in your calculator, get a decimal, that's fine. This is an exact value though, right? And so if in terms of our dimensions now, this is going to be one of the dimensions that we care about. Again, if you really wanted to be sure, right, you could put that on a number line. You could actually test to the left and the right. In this case, we want a minimum, so just make sure it goes from negative to positive, decreasing to increasing. Okay, but I'm going to go ahead and tell you, yes, it does. Okay, so that is the value that we wanted to get. Now, once we have that value, though, if we're looking for the overall dimensions here, what else do we have to do now? Yeah, we've got to plug that back in to solve for h. Well, we already know h is equal to this, so I'm just going to plug it in right there. We're going to have 1,000 divided by pi times that r value, cube root of 500 over pi, all squared. Now, if you get to that point, I am happy. Okay, so that value, even though you could simplify that fraction a little bit more, whatever, that's perfectly fine. Last thing I do want you to think about, though, what would the units be on our dimensions now? Okay, so think about it here, right? Centimeters squared measuring an area, right? The height and the radius, though, would actually be just centimeters because they're linear. So this is just going to be centimeters for radius and then centimeters for our height. Okay. So the volume was in centimeters cubed. The area itself would be in centimeters squared, but we're looking for the radius and the height. Those are just going to be centimeters. Any questions about that? Now, just so you know, if you did want to simplify this one, when you square this cube root here, one of those 500 over pi's is going to come out and leave you with a cube root. The pi's cancel out. 1,000 divided by 500 is 2. This actually just works out to 2 times the cube root of 500 over pi if you do the work, which means that the height then is actually just 2 times the radius, which is kind of a neat fact because in general, if companies are trying to minimize the cost of material for a cylinder, right, this is the formula they're almost always going to follow, right? If they make the radius half as much as the height, then that'll always minimize the amount of surface area that they need to create whatever they want to hold, okay, no matter what the volume happens to be. Any questions about that one now before we move on? Again, these types of problems, honestly, are one of the most practical applications of calculus out there in the real world, right? Because companies do this all the time. They're trying to think, how can we cut down our cost? How can we maximize our profits? And so they're always looking for ways that they can minimize the amount of stuff they have to use to package whatever they're trying to sell. So which one is the right answer? Either, right? So if you had gotten this one right here, that's fine. But even if you stopped right here, I'm perfectly happy with that answer. And then you would need the radius, which is this one right here. Okay, so those would be the 2 dimensions I'd be looking for. Again, if you wanted to simplify it more, right, where I have the arrow there is fine too. Any other questions there? All right. Now, again, we've talked about this before, but the first derivative test for absolute extreme values, suppose C is the critical number of a continuous function. If f prime of x is greater than 0 for all the x's less than c, and it's less than 0 for all the x's greater than c, then f of c is an absolute max. In other words, right, if it goes from increasing to decreasing around that value, then we know we have a maximum. And on the other hand, if it goes from decreasing to increasing, right, the f prime of x is less than 0, and then it becomes greater than 0, then we know we have a minimum of that value, right? So again, this is all stuff we've talked about, but again, this applies now to these optimization problems because we're typically looking for a maximum or a minimum value, okay? All right, example 3. We want to find a point on the parabola that's closest to the point 1, 4. All right, so what do you think we should do first here? Okay, so you could, right? We could solve for y. If you solve for y here, what are you going to get? Right, it's going to be square root of 2x, but what else do we have to remember in this case? Plus or minus, right? Okay, so because we took the square root there, we have to put a plus or minus in front of it. So you're actually going to get 2 square root functions, one that's positive, one that's negative, and by connecting those now, that's what's going to give us a parabola, right? So this is a parabola now that's turned on its side. Let me switch over to Desmos and I'll just show you what this graph looks like, and then I'll sketch it here so we can kind of keep that in mind as we're working through the problem. So again, in Desmos, you can actually put y squared in there. So y squared equals 2x. So there's your sideways parabola. Again, if you don't have Desmos and you're using your graphing calculator, you would have to solve for y. That would give us y equals square root of 2x. There's the top half. And then you'd have y equals negative square root of 2x. There's the bottom half. Okay, so we have to have both. So let me go ahead and, on my notes, I'm going to sketch that. Let's go through the point 2, 2 up here. So I'm going to try to make sure I hit that point. And then down at the bottom, it goes through to negative 2. I'm going to try to make sure I go through that point. All right. So there's our parabola. All right, so now that we know what the graph looks like, what can we do next? Let me ask this. Is there anything else we could put on our graph? One, 4, right? So we know the point 1, 4. I'm going to go ahead and put that up here. So there's the point, right? And we're trying to figure out now, where is the point on the parabola that's going to be closest to that given point at 1, 4? So again, this is an optimization problem, meaning we're trying to minimize or maximize something. So what are we trying to do this time? We're trying to minimize and so we would call that what? You said the line from the graph to the point, so that's the same thing as finding what? We're minimizing not slope. We're basically looking for what point on that curve now is closest to that point. Not normal line either, right? Because we don't know for sure that it's going to be perpendicular. So think about it this way, right? Let's say I'm going to the store, right? And I want to find the one that's closest. I want to minimize my what to the store? Distance, right? Okay, so that's all we're trying to do now is try to minimize that distance between the point and the curve. Because if we can minimize that, then we know we have the point that's closest, which means we're going to have to use distance formula. So distance formula, in case you've forgotten, is going to be square root. And we're going to have x2 minus x1 squared plus y2 minus y1 squared. Again, our first step, draw the picture if you can. We did that. Then you always want to figure out what formula are you working with, right? So that's our next step. In this case, we're trying to minimize the distance, so we're going to use our distance formula. Now, what are we going to have to do next? Okay. All right. We don't know for sure the point 2, 2 though, right? Because it could be any point on that curve. The only point we know for sure is 1, 4. It's fixed, right? It's not moving anywhere. So I am going to go ahead and plug in the 1, 4 in this case. And I'm going to let this be my x1 and my y1 value, right? It could be x2, y2. It really doesn't matter. Okay, but I'm going to go ahead and put it in as x1. So there's 1. and then I'm going to put 4 in for my y1. And so what we're trying to find now is the x and y value on the parabola itself that's closest to that given point. Okay, so that's why we can't plug in 2, 2, because we don't know if that's the closest point or not. All right. Good, right? At that point, we can go ahead and plug in now and actually get both of these variables in terms of the same variable. It's up to you which one you want to use. I'm going to tell you it's probably easier to solve for x in the original so that you're not dealing with a square root in here, because you're already got a square root around the whole thing, right? We don't want another square root in there. So I would probably come back up here now and get x by itself. So what would you have to do to get x by itself? Just divide by 2, right? So this is going to give us 1/2 y squared equals x now. Or y squared over 2. Either way is fine. Okay, but I would do it that way rather than trying to plug in the square root of 2x, just because then you're introducing a square root in there that's just going to make the simplification a little bit harder and the derivative. All right, so now in place of x then, I can put 1/2 y squared. So this is going to become 1/2 y squared minus 1 squared plus, and then this y2, I'm just going to make y minus 4 squared, because now I have everything in terms of the same variable. Any questions up to that point? Okay. Now, to make life easier, I'm going to go ahead and tell you that if we can minimize d squared, it's going to be the same thing as minimizing d. So I'm going to go ahead and just get rid of this square root by squaring both sides here and say that d squared is equal to 1/2 y squared minus 1 squared plus y minus 4 squared. Because otherwise, we're already going to have some chain rules in this one. Then you have a huge chain rule with the square root on the outside. And if we just minimize d squared, we should be good. It's going to give us the same x and y values that we would get, even if we did chain rule on the whole thing for distance. All right, now it's up to you, right? Either we can go ahead and take the derivative at this point using chain rules. We could simplify first if you'd rather do that. So you tell me, what would you prefer? All right, let's go ahead and simplify it then. So if we simplify this one, we've got 1/2 y squared minus 1 squared. If we square that, what's it going to give us? Okay, so that's what we should get, right? Because if we square this, we're just multiplying it by itself. And so those first terms are going to give us 1/4 y to the 4th. When we combine our outer and inner terms now, 1/2 and 1/2 just gives us a -1, so we're going to get a -1y squared. -1 times -1 should be +1. All right, what about the y minus 4 squared then? We square that, what are we going to get? Good. So y squared minus 8y plus 16. Now, go ahead and combine like terms over here. We've got our distance squared. 1/4 y squared doesn't combine with anything, so we'll keep that. Sorry, 1/4 y to the 4th. Now, if we combine our y squared terms, those are going to cancel, right? -y squared and +y squared. Then we're going to have a minus 8y, and then adding together the 1 and the 16 should give us a plus 17. All right, now that we've simplified it, now we need to do what? Now we can take the derivative. Good. So I'm taking the derivative of d squared. So what's that going to give us? Good. Just y cubed minus 8, right? Because the first term there, the 1/4 and the 4 just gives us 1. Drop your exponent by 1, that's y cubed. Derivative of 8y is just 8, and derivative of 17 becomes a 0. All right, so now we have our derivative. What's our next step going to be? Good. Now we can set it equal to 0 because we're trying to minimize that distance. So we're going to have 0 equals y cubed minus 8. How are we going to solve that? Good. Add our 8. So we get 8 equals y cubed. And then we can do what? Take the cube root. What's the cube root of 8? 2. Perfect. So now we know the y value is going to be 2. Now we're trying to find the point. So what do we have to do next? Plug the y value in, right? And it doesn't matter where, right? You can go back to the original equation. You could do the y equals plus or minus square root of 2x, or you can go up to the one that we got up here. This is where I'm going to plug in. So x equals 1/2 times y squared, which is 2 squared. And so if we simplify that now, what's our x value going to be? Two. Good. So now if we write that as an actual point, the point that we're looking for in this case is going to be 2, 2. There's the point that's on the parabola, right? We were, you were correct earlier in assuming it was going to be 2, 2. Okay, but that is the point on the parabola that's closest to the point 1, 4. Any questions on that one now? Okay. Now, what I will tell you is drawing the picture, right, actually sketching the graph, or just using Desmos at least to look at the graph is extremely helpful on problems like this. Because in some cases, what will end up happening is you'll end up getting, like, the work works out to show you that this point down here is the closest point. And you can look at the graph and say, well, no, it's not, right? That answer doesn't even make sense. Okay, and so then you would know, oh, yeah, it's got to be the one that's up here. Because sometimes you'll get like a plus or minus value as you're actually solving. Let's say you were taking a square root after you set it equal to 0, something like that, and you get a plus or minus. To be able to determine which value you actually want to use, look at your graph and figure out which one is actually closer to the point that you care about. Okay. All right. Example 4. So, a lot of words here. Okay, I'm just going to read through it, and then we'll try to see what we can pick out of this. We'll sketch our picture. We'll find our formulas. We'll work through it the same way. Okay. So a man launches his boat from a point A on the bank of a straight river. The river is 3 kilometers wide, and he wants to reach a point B 8 kilometers downstream on the opposite bank. He wants to do that as quickly as possible. His options are: he could row his boat directly across the river to point C and then run to B, or he could row directly from point A to point B, or he could row to some point between C and B and then run to B. Okay? So those are his 3 options, right? He's got to get across the river and he's got to get downstream. So he could either go directly across and down, he could go to some point in between and down, or he could row directly to that point. Those are his 3 options. However, he can row at 6 kilometers per hour and he can run at 8 kilometers per hour. It should be where. So we want to know, where should he land to reach B as soon as possible? And we're going to assume here that the speed of the water is negligible, so it's not like a flowing river that's going to push him downstream faster or anything like that, compared with the speed at which he rows. Okay. Now, first step, we need to draw the picture. So what can we put in our picture first? Okay, so we know we've got a river, right? So I'm going to draw my river here. It says the river's straight. Has some width to it. We don't know exactly how wide. Okay. Or actually, we might actually know that. So we'll put that in there. It is 3 kilometers. Good. Okay, so across here now, we know the river is 3 kilometers wide. All right. What else do we know? Okay, he needs to go downstream 8 kilometers, right? So let's assume in this case that he's starting up here in the top left corner. That's going to be point A, right? That's his starting location. He's trying to reach point B, which is on the opposite bank and 8 kilometers downstream. So I'm going to put point B down here, and this total distance to point B is going to be 8 kilometers. Okay. Now, his 3 options. He could go from A to, let me make sure I put the right label there. Point C would be right here directly across. He could row to some point in between, which we're going to call D. And then he could run down to B. Or he could row directly. These should be straight lines. Sorry, they're not perfect. Okay, directly from A to B, right? Those are the 3 options: straight across and down to B, from A to D and then down to B, or directly from A to B. All right. What are we trying to minimize this time? So we're not necessarily trying to minimize distance, right? Because the shortest distance is definitely going to be from A to B. We're trying to minimize the amount of time because he rows and runs at different speeds, right? So how would you relate all of this stuff together if the thing we're trying to minimize is time? do we have a formula that relates all the information together that we know so that we can solve for time? Okay, good. Speed is equal to distance over time. It's like miles per hour would be a distance over a time. That gives you a speed, right? So that's the formula we're going to have to use. Now, again, the thing we're trying to minimize is time. So let's get time by itself here. So how would you get time by itself? Good, right? Multiply by time, divide by speed. That's going to give us time equals distance divided by speed. So that's the formula we're going to work with now. That's the thing we're trying to minimize. Now, again, our goal is going to be to get everything in terms of the same variable here before we take our derivative so that we can easily minimize that amount of time. We've got 3 different scenarios, though. So what we need to try to figure out is how can we get them all into a single scenario where we can use a single variable and not have to worry about which one he's actually going to do. So the way we're going to actually do that in this case, I'm going to use just x as my variable, right? Just try to get everything in terms of x. So I'm going to say, let's let this distance between C and D be equal to x. That way, D could be anywhere between C and B. It could technically be, x could be 0 and it would be right on top of C. X could be 8 and it would be all the way down at B, right? So it takes care of every possible scenario between C and B, including C and B. If that's the case, though, how far would it be from D to B? Almost, I think, yeah, it should be 8, right? Sorry, this is an 8. Let me make sure that's clear. This is 8 kilometers downstream, so this is going to be 8 minus x now. Okay, good. Any questions about that? We're letting distance between C and D be some variable x, which means the remaining distance is the 8 kilometers minus that x value. Now, all we really need to know at this point then is how far is it from A to D? So how could we find that distance now from A to D? It's a right triangle, right? So we have a right triangle right here. So we can use what to find that distance from A to D? It's Pythagorean theorem, right? So we know the 2 legs, right? One of them is an x, that's fine. We just want to get everything in terms of x here, though. I'm going to call this hypotenuse y. So that means that y is equal to, y squared would be equal to 3 squared plus x squared. And so now if we simplify that and we take the square root to get y by itself, the distance between A and D is just going to be the square root of 9 plus x squared. So now I know this distance right here is the square root of 9 plus x squared. And that was just using Pythagorean theorem to find that in terms of x. Well, now we have all of our distances, right? All the possible distances in terms of x. That's what we need in our numerator. The other piece that we're going to need is speed. Do we know the speeds for each of those distances now? Yeah, right. So we know in this case that he can row at 6 kilometers per hour. So that's going to be that distance from A to D. He can go 6 kilometers per hour. And then he can run 8 kilometers per hour. So that's going to be what he's doing along the bank over here from D to B is going to be 8 kilometers per hour. And again, the X itself takes into account he could land D anywhere he wants on the opposite bank. Right? We make X0, he lands at C. We make X8, he lands at B. We make it anything else, he's going to land somewhere in between. Okay. So now let's see if we can actually figure out his time in terms of X. So how would you figure out his total time now? Okay, so before we do the derivative, right, we need to get everything in terms of the same variable. We're going to get everything in terms of X. So let's get that time in terms of X first before we take our derivative. Let's just start with his rowing, right? So we know he's going to row from point A to point D, wherever D happens to be on the opposite bank. What's the distance from A to D? The square root of 9 plus x squared, right? So that gives me my distance for my numerator. So square root of 9 plus x squared. Then we're going to divide that by speed. What's the speed going to be for that distance? That's the 6, right? Because that's his rowing from A to D. He can row at 6 kilometers per hour. So there's our speed. Now, that's not all he's doing, though, right? He's also going to run down the opposite bank. So what are we going to have to do now? What's his distance down the opposite bank going to be? Okay, good. It's going to be 8 minus x as his distance. The speed that he can run is 8 kilometers per hour, so that's his speed down there. And now we have the time it takes him to row, the time it takes him to run. And so if we add those two times together, that's going to give us his total time. That's the hard part. Okay, so we're done with the hard part of this problem. Getting it set up, just thinking through all the possible scenarios in this case and trying to get everything in terms of the same variable, that's what's difficult. Okay, because now we have a time formula just in terms of x. What are we going to do next? Okay, well, we can't solve for x, right? Because we don't actually know what time is. So we're trying to minimize the amount of time here. We're trying to do this in the shortest amount of time possible. So what are we going to have to do with this formula now? Take the derivative, right? Okay, so I'm going to go to a new slide. I'm going to keep this time formula that we just created, and then we're going to look for our derivative for that. All right, so what we had was time equals square root 9 plus x squared over, oops, that was 6 plus, and then this was 8 minus x divided by 8. All All right, so if we're going to take the derivative here, what do you want to do first? All right, so pull out the constants. All right, so in this case, the 6 in the denominator, I can actually just write this as 1/6 out front. And then what can I actually do with the square root now? Make it a 1/2 power, right? So I'm going to rewrite this now as 9 plus x squared to the 1/2 plus. Now, what about this fraction over here? What could I do with this one? Okay, so it's not going to just be minus x, right? Because we have to divide each of our terms. So, and it's not going to be 1 minus x either because we have to divide each one of them by 8. Okay, so you're closer there, because 8 divided by 8 would give us a 1 minus, but then if we divide the x by 8, that's going to leave us with what? Good, x over 8 or 1/8 x. So that's what I would do here first. Go ahead and simplify that. That way we don't have to use a quotient rule or anything, right? Since we have a nice number in the denominator, just go ahead and simplify them. Any questions about that? The second term, are you looking at, let me make sure, the 1/8 x, or you're asking about the entire thing, the 8x over 8? Okay. So what I did, let me go back to the previous slide here. So we know that the distance between D and B is going to be 8 minus x. And then we know that the speed that he can run is 8 kilometers per hour. Oh, in the derivative? So the 8 minus x over 8. So the one, okay. So I'm basically just dividing 8 over 8 minus x over 8. So I'm splitting those up into two separate fractions. And so then 8 over 8 gives us the 1, and then x over 8 gives us the 1/8 x. Okay. Any other questions there? Yep. All right. So now we can actually take our derivative, right? So we need to go through and think about what this derivative is going to give us. So how are we going to find the derivative for this first piece? Okay, good. It is going to be a power rule combined with a chain rule. So we're going to take the 1/2, we're going to multiply it by the 1/6. That's going to give us 1 over 12. Keep everything inside, 9 plus x squared. What's our new exponent going to be? Negative 1/2, because we have to subtract 1 from that exponent. And then we have to multiply by the derivative of what's inside. What is the derivative of the inside? Just 2x. Good. So there's our derivative for all that first stuff. And again, if you want to do out to the side, u equals 9 plus x squared, find that derivative, do everything in terms of u, feel free, right? But if you can do it like this, that's fine also, because this derivative inside is not too bad. All right, now what's the derivative of 1 going to give us? 0, right? And the derivative of negative 1/8 x, negative 1/8. So we get a minus 1/8 down here now. All right, now The only thing we can really clean up in this one over here at this point, we can multiply the 1/12 times the 2x, and then I can move the negative 1/2 exponent to the denominator. 2 times 1/12 is 1/6. So now we're going to be left with x over 6 times 9 plus x squared to the 1/2 power. And then our minus 1 over 8. Any questions about how I got that? All right, now that we have the derivative, what do we need to do next? Set it equal to 0. Good. So we're going to say 0 equals, just keep this as is, x over 6 plus 9, or sorry, 6 times 9 plus x squared to the 1/2 minus 1/8. Now, what are we going to do first to solve this? Okay, good. We can move the 1/8 over, so that's going to give us 1/8 equals x over 6 times 9 plus x squared to the 1/2. What would you do next? Good. Since we have a fraction equal to a fraction, we can actually just multiply, cross multiply to get what we're going to have on each side. So 8 times x in this case is going to give us the 8x. And then 1 times the other denominator is just going to give us what we've got down there. So that's going to be the easiest way in this case to get rid of those fractions and then be able to solve for x. All right, what do you think we should do next? Okay, good. Divide by your 6, right? So that's going to give us 8 over 6, which simplifies to 4/3. We have 4/3 x equals 9 plus x squared to the 1/2. Okay, what do we need to do now? Okay, good. Now we can square both sides to get rid of that 1/2 power, right? Because that's the same thing as a square root, so we're going to square both sides. What's 4/3 squared going to give us? Good, 16 over 9, right? So I'm going to bring this up here now. So we get 16 over 9 x squared equals, and then over here now we're just left with 9 plus x squared. That's after we squared both sides. All right, what's next? Okay, good. We can move the x squared over to combine it with the x squared on the other side. What's 16/9 x squared minus 1x squared? Good, right? So 16/9 minus 9/9 is going to leave us with 7/9 x squared equals 9. All right, what do you want to do next? Okay, good, right? So either divide by 7/9, same thing as multiplying by 9/7. So that's going to leave us with x squared equals, and this becomes 81 over 7 now. All right, so then what do we have to do? Good, take your square root. So x equals, square root of 81 is just going to give us 9 in the numerator. And we can't take the square root of 7, so we'll leave that as a square root of 7 in the denominator. Now, because this x represents a distance, we don't need a plus or minus, right? So technically there would be one there, but for this one, real world wise, right, we don't need it because we're looking at a distance. All right, so now going back to the picture, right, the x value was this piece right here. We wanted to figure out where should he land, which means he wants to land downstream this distance right here. What would be our units? Okay, so we've minimized the amount of time, but we're trying to figure out where on the opposite bank he needs to land. So that's actually going to be that x value over there is going to be measured in what? Kilometers, right? So we know the total distance over there is 8 kilometers. We're looking for the distance between C and D, so that's just going to be kilometers. So now this is 9 over the square root of 7 kilometers. That's where he needs to land his boat to minimize the amount of time that it would take him to get to point B. Any questions on this one now? Now, before you flip out, I would never give you a problem like this on a test, right? Okay, this one's extremely involved. It takes a lot of time. Okay, but there could be some in the homework like this for the optimization section. So just make sure, again, just like with related rates, leave yourself enough time for that homework because some of them you will have to think through. You know, figure out first, draw the picture, figure out what formulas you're going to use, get everything in terms of the same variable, find your derivative, but again, this one in particular, figuring out how to get everything in terms of that same variable, I think is the trickiest part. The derivative's not easy, right? But it's not too bad. And then you just have to solve for x at that point. Okay. All right, so that's the end of that section. Like I said, that's all we're going to do in that section anyway. Let's take our break here. So I've got 11:07, so 11:12 we'll come back and we'll get started on section 3.9. All right. So 3.9 antiderivatives. Again, this is the last section we're going to cover here. So we'll get through as much as we can today. Whatever we don't finish, then we'll save for Monday. And then again, we'll review on Monday also. Okay. So antiderivatives is what we're looking at. All right. So a function f, and we're using a capital F in this case, is called an antiderivative of little f on an interval I if the derivative of big F is equal to little f. In other words, we're basically working backwards now, right? So instead of finding a derivative, we're given what the derivative function would be, and we're trying to figure out what that initial function would have been if that's the derivative, okay? So the big F now is basically working backwards to an original function where we are given the derivative of that function. Now, if f is an antiderivative of f on an interval I, then the most general antiderivative of little f on that interval is big F of x plus c. And if you remember, we had a theorem or a corollary earlier that basically said, well, yeah, the derivative at a bunch of different points can be the same for two functions. They're just translations of one another, right? Okay, because the slopes of the tangent lines would all still be the same. I'll show you again the graph. If you had something where, you know, the bottom part looked like this, and then you had the same thing going on, but up here, the derivatives of both of those graphs are going to be identical, right? But one is just a translation of the other. And so that's why we need this plus c when we find our antiderivative, because there could be some arbitrary constant there that we're not aware of. Okay? But the derivative of that constant is always going to give us 0 no matter what. And so that's why its derivative would still be the same. All right, so let's take a look at these examples here. So again, all we're doing, we're given little f of x, we're trying to find big F of x, which would be the original function whose derivative would be equal to little f of x. So what function would you have to take the derivative of to get sine of x? That's what we're asking ourselves. So what would the initial function have to be in this case? Okay, all right, it is going to be negative cosine x, because remember the derivative of just cosine would be negative sine, so we need to make it a negative now so that its derivative would give us positive sine. Okay, now again, whenever we're looking for the most general antiderivatives, what else do we always have to remember to put on our antiderivatives now? Let's see. So don't forget this arbitrary constant here, because now when I go through and take the derivative of cosine is negative sine, right? So it's going to give us negative sine of x. Derivative of a constant is 0, so that goes away. And so then this would actually give us sine of x, which is what we started with. Okay. Any questions about how we got that as our antiderivative this time? So again, f prime would be equal to this, but this is what we're actually looking for. Okay. All right, let's take a look at the next one now. So again, if little f of x is x to the n, we want to figure out what would the initial function have to be to give us that as our derivative. Okay, good, right? So basically, right, we're working backwards. So instead of subtracting 1 from our exponent, we're going to want to add 1 to that exponent. So that's where the n plus 1 comes from. But then we're going to need a coefficient out front here to account for the fact that that n plus 1 is going to come out front. So we have to put a 1 over n plus 1 out front now. Okay. And then we do need our arbitrary constant, so we need a plus c. So again, if we were to find the derivative of that now, we would bring down the n plus 1. N plus 1 over n plus 1 just becomes 1, so that goes away. Then we would have our x value. We would subtract 1 from that exponent, which would leave us with an n. and then the derivative of the constant is just going to give us 0. And so now that's what we started with. So this is our antiderivative for that one now. Now keep that one in mind, because this is going to be a generic formula for us moving forward. Anytime you have x to some power, this is what we're going to do. We're going to raise the exponent by 1, but then we have to remember to put that coefficient out front, 1 over whatever that new exponent is. Any questions there now? All right, so part C, same thing. We're trying to find the initial function whose derivative would give us x to the negative 3. So what do you think that's going to look like? All right, so we're going to have an x to the negative 2 for sure, because we're going to add 1 to the negative 3. And then out front here now, we do 1/2, right? The 2's would cancel out. I agree with that. But what else are we going to need here so that we end up with just a positive x to the negative 3? There needs to be a negative out front also, right? So make sure you make that a negative. So now we get negative 2 times negative 1/2. That's going to give us a positive 1 out front. Subtract 1 from your exponent. That's going to give us the negative 3. And again, we do need that positive c as our arbitrary constant. But again, if you take the derivative of this now, negative 2 times negative 1/2 is just positive 1x to the negative 3rd power plus 0. Any questions on that one now? And that follows that same pattern as part B, right? So we're adding 1 to the exponent, and then we're putting 1 over that new exponent out front. It's 1 over negative 2, which is where the negative 1/2 comes from. All right, now just some general antiderivative formulas to keep in mind, especially for your trig ones over here. Those are going to be important to remember. Okay, but if you have some constant times a function, right, the antiderivative is just going to be that same constant times its antiderivative. Okay, so just keep that in mind. There's a constant, you can almost just ignore it and just find the antiderivative of the function itself. You have the sum of two functions, same thing, we can find the antiderivative of each one individually and just add those antiderivatives together. And then this x to the n, assuming here that n is not negative 1, okay, because we'll have a different antiderivative if that's the case. Okay, but as long as that's not a negative 1, we're just going to add 1 to the exponent and then divide by whatever that new exponent is. Or again, the other way to write that would be 1 over the n plus 1 times x to the n plus 1, right? Those are the same thing. All right, now our antiderivatives for our trig functions, cosine just gives us sine, right? Because the derivative of sine would be cosine. We're finding the antiderivative of sine. We do need a negative cosine so that we get that double negative there to give us a positive sine. Antiderivative of secant squared is tangent, because again, the derivative of tangent would be secant squared. Antiderivative of secant tangent is secant, because the derivative of secant gives us secant tangent. So in those cases, right, if you know your derivatives, the antiderivatives shouldn't be too hard. You just have to be really careful, right, because we are doing both derivatives and antiderivatives in the same unit. So just make sure you pay attention to which direction you're working. That's the main thing, okay? Any questions on those formulas? All right. So let's take a look at this one now. So we want to find all functions g, so basically the general antiderivative, so that the derivative here would be equal to 4 sine of x plus 2x to the 5th minus square root of x over x. Okay. Now, what do you think we should do first in this case to help us find our antiderivative? Good, right? So we need to simplify this fraction because we don't have a way to find an antiderivative of a quotient like that, right? We don't know how to do that. So what we're going to want to do first is simplify that. Now, in this case, you could just move x to the top, make it an x to the -1, or you could just say, well, it's the same thing as dividing each of our terms now by x. So let's do that. If we divide each term by x there, keep our 4 sine of x, plus, what's 2x to the 5th divided by x? 2x to the 4th. Good. And now if we divide the square root of x by x, what are we going to get? Good, right? So we have our minus here, and then x to the -1/2. Because again, this is the same thing as x to the 1/2 over x. And so if we subtract those exponents now, 1/2 minus 1 will give us -1/2. So anytime you can simplify that first, go ahead and do that. Now let's see if we can go through term by term and find the antiderivative. The antiderivative this time is just going to be g of x, right? Because we're looking for the function whose derivative would be g prime. What's the antiderivative for 4 sine of x? Good, right? So antiderivative of sine is negative cosine. So we're going to get a -4 cosine x plus, how are we going to find the antiderivative for 2x to the 4th? So what if this was just x to the 4th? How would you find the antiderivative of just x to the 4th? Okay, add 1 to the exponent, right? So that's going to give us x to the 5th. And then we're going to divide by the 5, right? Or put a 1/5 out front. And then we can keep the coefficient that was already there, right? Okay, so that's probably the easiest way to think about it. Keep the 2, raise your exponent by 1, and then we're going to multiply by 1 over that new exponent. So that's where the 1/5 comes from. Okay? Any questions about that term? We will come back and simplify that. 2 times 1/5 is 2/5, right? Okay, but for right now, if you just keep the 2 and then think about x to the 4th, what's its antiderivative, we can do it that way. Now let's get our last term. So we have our minus. What's the antiderivative of x to the -1/2 going to give us? Good, right? So we're going to have an x to the +1/2 because we add 1 to the exponent. Then we have to divide by the new exponent. So this is like 1 over 1/2. But remember, when you divide by a fraction, you're multiplying by its reciprocal. So that is going to give us a 2 once we simplify it. And then with all of our antiderivatives, we have to have what here at the end? Plus c, right? And we only need 1 plus c at the end because it is an arbitrary constant. So even though technically we could put a plus c on every one of those, once you combine all those constants, you're going to get a constant there at the end anyway. All right, so now I'm just going to clean this up. So g of x, we have -4 cosine x plus, it's going to be 2/5 x to the 5th. And then like we said, 1 divided by 1/2, same thing as 2 x to the 1/2. And then we have our plus c. All right. Again, I'm actually going to change this on this line just so it's clear. We keep the 4, antiderivative of that is negative cosine x. And that's how I got the -4 cosine x for that one. Any questions on that antiderivative now? No, we're not secretly doing integrals because we haven't talked about integrals yet. And this is technically not the same thing, right? So be careful. Yes, these are going to come into play when we get there, right? But antiderivatives and integrals are not equivalent to each other, right? They're not the exact same thing. So just be careful how you talk about those two things. Any other questions here? All right. Now, the nice part about antiderivatives, right, it's very easy to check your answers because we know all of our shortcuts for derivatives. So if you just take the derivative of your final answer here, it should give you back what you started with. Right? So always feel free if you're unsure if you've done everything correctly, just take the derivative of your final answer and it should give you the function you started with. Okay, or at least in this case, get you back to here. Okay. All right, so again, we're looking for the antiderivative if our derivative is x times square root of x, and in this case, they give us a point f of 1 equals 2. All right, now, what's the first thing you think we should do in this case to help us find our antiderivative? All right, so let's go ahead and change this then to x to the 1/2 power. So we got f prime of x equals x times x to the 1/2. Good. And what can we do now? So is there any way I could simplify what we've got there? Okay, so it is a product, right? So we don't know, again, how to deal with products in terms of finding antiderivatives. So let's just go ahead and multiply that together. What's x times x to the 1/2? Yeah, we're just going to get x to the 3/2 power in this case. So always simplify your derivative as much as you can first before you try to find your antiderivative. Well, now we can find the antiderivative. So what's that going to look like this time? Perfect, right? So we're going to add 1 to the exponent first, right? So that's going to give us x to the 5/2. And then remember, it's 1 over that new exponent, so that's 1 over 5/2. Don't forget your plus c. But again, whenever we're dividing by a fraction, we're just multiplying by its reciprocal. So this becomes 2/5 x to the 5/2 power plus c. So there is our antiderivative. Now, in this case, they actually give us some more information so we can find the specific antiderivative for this one. So since we know that f of 1 equals 2 now, what could we do? Okay, good. We can actually solve for c by substituting those values in. So what are we substituting in place of f of x then? So not 1, because 1 is the what value? Okay, good. 1 is our x value. 2 is the f of x value. So this is going to be 2 equals 2/5 times 1 to the 5/2 plus c. So now we can solve for c. If we simplify 2/5 1 to the 5/2, what's all that going to give us? Just 2/5, right? Because 1 to any power is 1. 2/5 times that is going to give us 2/5. And now if we get c by itself, what are we going to get? Eight over 5, right? Because 2 would be the same as 10/5. We're subtracting 2/5. This just becomes 8/5 is our c value. Okay? All right. Now that we have the c value, now I can come back up here and just substitute that in place of c. So my f of x is going to be 2/5 x to the 5/2 plus 8/5. So this is the specific antiderivative based off the information that's given. So anytime they give you a point or something like that, you are going to find a specific function. There's not going to be a plus c anymore because you're actually going to solve for that c value. Any questions on that one now? Again, always look for ways to simplify that derivative first, okay, so that you can actually take the antiderivative of whatever you got. All right, now this time we're trying to find f. They give us that f double prime of x is 12x squared plus 6x minus 4. And this time we actually know two pieces of information. F of 0 is 4 and f of 1 is -1. All right, so let's just start here. If we know the second derivative and we're trying to find the initial function, what are we going to do first? Good, right? If we find the antiderivative, that's going to give us f prime this time, right? So just finding the antiderivative once will move us back to f prime. Well, what's our first antiderivative going to give us this time? All right, so 4x cubed is going to be the first term, right? Because we're going to have our 12 out front, raise your exponent by 1, multiply by 1 over that new exponent. 12 times 1/3 would give us 4, right? So that's going to give us 4x cubed. Good. What about the next term? Okay, it's going to be 3x squared because, again, if you want to see the steps, it's 6 times. We raise the exponent by 1, multiply by 1 over the new exponent. 6 times 1/2 is 3, so 3x squared. And then finally, the last term here is just going to be 4x. The derivative of -4x would just be a -4. Right. Then what else do we need here on any of our antiderivatives? Plus c, right? So we need that constant. And then if we go through and just simplify all this, it will give us those terms we just said. 12 times 1/3 is 4x cubed. 6 times 1/2 is 3x squared. We have our minus 4x, and we have our plus c. Now, do we have anything that we can substitute in at this point? No, right? We're not given any information about f prime, so we can't substitute anything in. We need to get all the way down to f of x to be able to substitute any of that information in there. So now what are we going to do? Okay, now we can find f, right? So we're going to find the antiderivative of that first derivative to take us back to f. Now, what's that first term going to look like if we do its antiderivative? Okay, so we're going to get x to the fourth. Good. So again, if you need to see the steps, keep the 4, raise the exponent by 1. That's an x to the fourth. 1 over that. But again, the 4 and the 1/4 will just give us 1. Plus, keep the 3, raise the exponent by 1, multiply by 1 over the new exponent. Minus, keep the 4, raise the exponent by 1. That's x squared. And then we have a 1 over that new exponent. And then the last term here is a constant. Its antiderivative then is going to be plus c times x. Right? Because if just like the 4 before gave us a 4x, in this case the c is going to give us a cx. And then we need some other arbitrary constant down here, and so we can just use d in this case as our second arbitrary constant. Any questions about how I got any of those? All right, so now I am going to simplify this. We have 4 times 1/4 is 1, so we get x to the fourth. 3 times 1/3 is also 1, so that just gives us x cubed. Minus 4 times 1/2 is a 2, x squared. Then we have plus cx and plus d. So now our goal is going to be to find c and d so we can find the specific function whose second derivative would be what we got there. Okay, and it has to go through these points. So what do you think we should do first? You could, right? So in this case, though, because of what's given, you don't even have to go as far as creating a system. We know f of 0 equals 4. We can actually plug in that point first, and it's actually going to give us what we want. Okay, so if you were given like f of 1 equals something and f of 3 equals something, yes, you'd have to create a system of equations. I'm never going to go that far, though, just because I'm more interested in can you find antiderivatives, right? Not can you work with systems. So if we plug in that first point, what's our f of x value going to be? 4, right? So 4 equals, and then what's our x value? 0, right? So everywhere I see an x, I'm just going to put a 0. So 0 to the fourth plus 0 cubed minus 2 times 0 squared plus c times 0 plus d. So again, because one of the x values was a 0, it's going to make all the x's go away, right? And so what's our d value going to be this time? Just 4, right? So we've got 4 equals d now. All right, so now that we know that, I can write f of x is x to the fourth plus x cubed minus 2x squared plus cx plus 4. Now we have another point that we can use to help us find the c value. So what's our f of x value going to be this time? -1, good. And our x value is going to be what? +1. So now we have 1 to the fourth plus 1 cubed minus 2 times 1 squared plus c times 1 plus 4. So c times 1 is just c. So now if we combine everything else that we've got over here, we've got 1 to the fourth is 1, 1 cubed is 1, minus 2 times 1 squared is minus 2, and then we have our plus 4. So what are we going to get on that side? Just 4, right? Because 1 plus 1 minus 2, that all cancels. And so we're left with c plus 4. And so what's our c value going to be this time? -5. Good. Right. Now that we know the c value and the d value, now we can just write the entire function. So we have f of x is x to the 4th plus x cubed minus 2x squared minus 5x plus 4. So this is our specific function for our antiderivative that goes through the 2 points that are given. Any questions on that one now? All right. So this time they give us a graph, right? And they're telling us that this is the little f. We're trying to find big F. So we just want to sketch a graph. And they tell us here that the point on our big F function at 0 is 2. So we've done something similar where they give us the original function, we find the derivative graph. Now we're working backwards, right? They're giving us the derivative graph. We're trying to figure out what that initial function would have looked like. Well, where are we going to start? Okay. So before we even do that, right, let's look at the information that's given. So we know that big F of 0 is equal to 2. So where can we start our graph? At 2, right, on the y-axis. So there's our y-intercept. I'm going to come up here to +2. I'm going to put a point. Okay. So that's where we're starting from. Now let's look, okay, and think about what we know. So you said look at the x-intercepts, okay? So what are the x-intercepts going to tell us then? So if the blue graph here represents our derivative, and we're trying to find the original function, what would the x-intercepts represent? So what's the value of the derivative at those x-intercepts? 0, right? Okay, so the value of the derivative at those points is 0. If the derivative equals 0, what does that tell us about the original function? Those are your critical points, right? And what do we know about critical points? What could we have at critical points? Maxes and mins, right? Okay, so as long as it goes from increasing to decreasing or decreasing to increasing around those points, then we're actually going to have a min or a max value. Okay, so this tells us what the critical numbers are, and then we can look for where it's increasing, decreasing now to determine if there actually is a min or a max there. Well, let's look at the left-hand side of 1 here, right? So our derivative, I'm looking at this section over here. What do we know about the derivative over here now from 0 to 1? Okay, the derivative itself is increasing. I agree with that. However, is the derivative positive or negative here? It's negative. If the derivative is negative, what does that tell us about the original function? Okay, slope downward means it's doing what? Decreasing, right? So what this tells us now is the original function along this interval is decreasing. Now, once we get to 1, we hit 0, and then everything between 1 and 3 is in the positives. So what does that tell you about your graph from the interval 1 to 3? It's increasing now, right? So everything in here from 1 to 3, because the derivative is positive, everything on your original graph has to be increasing there. Then when we get to 3, it's 0 again. So there's another critical number. And then beyond that point, everything is below the x-axis, which means the original function is doing what? Decreasing again. Okay? So now we know our original function goes from decreasing to increasing around 1. It goes from increasing to decreasing around 3. So what can you say about 1 then? What's going to happen at 1? There's a local minimum there. Good. So we have a min at 1. And then it goes from increasing to decreasing around 3. So what can we say about 3? That's going to be a max. Good. So that's what you want to do with these, right? Is figure out, okay, I know the x-intercepts are where the derivatives equal to 0. Those are my critical numbers. If it switches from positive to negative around those points, then I know I have a max or a min. So then you just need to figure out, well, negatives are decreasing, positives are increasing, figure out those max and min values. Now that we know that, we know where our function starts. We start up here at 2, and we have to start off by decreasing from 0 to 1. Okay, so this is just going to be a rough sketch. We don't know exactly how far down or anything we're going, but we just know it's going to be decreasing until we get to 1. Then there's a turning point because it starts to increase. It's going to increase all the way until we get to 3. And then once we get to 3, then it's going to start to decrease again. And notice here, it's going to continue to decrease all the way to the, this could go on forever. We don't know. Okay, but at least until the end of that domain that's shown, it's going to decrease. But it slows down in how it's decreasing as we get towards the end here. Okay, so you probably want to kind of level that out. Okay, but that way we have our minimum here at 1. We have our maximum up here at 3. We're decreasing, increasing, and then decreasing again, okay, in each of those intervals. All right, so we are out of time. So that's where we're going to stop. We've got a few more examples to finish up here on Monday, but that's no problem. And then we'll spend the rest of the time going through the practice test. Again, if you want to start looking at the practice test, it has been posted. Don't forget the homework on 3.4 and 3.5 due by midnight tonight if you haven't finished that already. And then 3.7 and 3.9, go ahead and be working on that. I'm probably going to move it to Tuesday at midnight, but at least go ahead and be working on that once you finish the 3.4 and 3.5 homework, okay? Let me know if you've got any questions. Have a great weekend, and I will see you all on Monday.